In this lesson, we will continue with our discussion of rotational motion, and primarily we will discuss what is the cause of rotation. Well, what is the cause of linear motion? We know that a net force acting on an object will produce an acceleration that is the cause of linear motion. In the same way, what is it that makes an object rotate? Now, I'm going to produce rotation on this object. Now, this is the object on which I'm going to produce rotation. You can see I am producing rotation. All right, tell me, what is the cause of this rotation? Well, I know most of you will tell me it is a force. Yes, of course, I am applying a force. But a linear force that we are familiar with in previous lessons is not what is happening here. Now, the force I am applying is producing what you call a torque. Therefore, what makes an object to rotate is a torque. Now, I will write down that in a minute, but let's talk about this. So, what is the cause of rotation? The cause of rotation is a torque. Now, what is torque? Torque is caused by a force. Now, suppose I want to produce rotation on this object. If I apply a force directed downward, you can see that directed downward force is going to rotate the object, producing rotation. Now, when the object is here, if I apply a force downward on it, will that force produce rotation? No. So there are a couple of things that you need to understand about rotation. First of all, a rotation always occurs about an axis. Now, what is the axis of rotation of this object? The axis of rotation, let me see if I can show that to you. Now, this is the axis of rotation. You see that? This object is now rotating about this axis. In other words, the axis of rotation is at right angles to the plane of rotation. Now, if I want to produce a rotation about this axis and I'm applying a force at right angles here, the torque produced by this force depends on this distance. You see, if I apply the force very close to the axis here, will it produce any rotation on this? Very little. And finally, if I apply a force here on the axis, will it produce any rotation? No, it is not producing any rotation. So, the torque, the rotation effect, which is we call the torque. The torque depends on two things. One, the amount of force and the perpendicular distance between the force and the axis of rotation. Again, if this is the axis of rotation and the force is directed downward, the perpendicular distance between the force and the axis of rotation is this distance. And this distance is called the torque arm. Alright, now tell me, if I have the object in this position and I'm applying a force downward and I'm rotating the object about this axis, well, what is my torque arm now? The force is vertically downward. Is my torque arm this distance? No. My torque arm now is this distance. In other words, if you consider a vertical axis there, the perpendicular distance between the direction of the force and that vertical, this is now the torque arm. If this distance is r, this will be now r sine theta, where theta is this angle. Now that means as this object comes closer and closer, what is happening to the torque arm now? The torque arm now is decreasing. That means when the object is here, the force that is directed downward will produce no torque at all. The torque arm is now 0. But now if I move it now like this, the torque arm is increasing. This distance is increasing. And when it is at 90 degrees, this is my torque arm. So there are two things that determines the torque when a rotation takes place. What are the two things? The two things are, one, the amount of force. The other is the torque arm. Alright, let's put that down in writing. I think I took more than. As we discussed earlier, a linear acceleration A is caused by a net force F net. The second law of motion is equally applicable to rotational motion. Rotational acceleration alpha is caused by a net torque. And we write torque, represent torque by the Greek letter tau. Let me write that for you. Now, tau is written like this. Pronounce it tau. So, the rotational acceleration alpha is caused by a torque, tau. Now, you are familiar with this situation. Here you have a screw. If you want to rotate that screw, you have to apply a torque. Now, I have a lever here which I can put into the groove and then turn the screw. A force F applied at right angles to the handle of the screw produces a rotation on the screw about an axis. What is the axis of rotation? Look at the axis of rotation. So just like I just demonstrated, the screw is now rotating about this axis. And now the force is applied at right angles to the handle. The perpendicular distance between the force F and the axis of rotation is this r. This is the perpendicular distance between the force and the axis of rotation. And I told you that that distance is called the torque arm. Okay? The torque tau produced by the force F about the axis of rotation is tau equal to r times F, the torque arm multiplied by that force. And that is a measure of the torque. Well, r is called the torque arm. Actually, the torque arm is a vector. This r is a vector. The force F also is a vector. Therefore, r times F is the product of two vectors. Now, do you remember in few classes ago, 2 or 3 classes ago, we multiplied two vectors to produce work done. Work done by a force is the product of the force and the displacement it produces. Force is a vector quantity, displacement is a vector quantity, therefore work done is the product of two vectors. And we call that product by a name. What was that? It is called the dot product. Now here, this tau is the product of two vectors. Now there is a difference between this product vector and the product vector we considered earlier, because work done is a scalar quantity. We found earlier that force vector multiplied by the displacement vector gives you work done, which is a scalar, and we call it the scalar product or the dot product. But the torque of a force is a vector. So the vector r multiplied by vector f is the torque, which is a vector. So this is called the vector product of two vectors, or sometimes called the cross product. Now, so r is a vector drawn from the axis of rotation, and f is also a vector. What happens if the force F makes an angle theta with the vector r? Now, if this force now makes an angle theta with the vector r, then you can see this r is no longer perpendicular to the force. Now, in order that this definition may be true, r and f has to be at right angles. The force must be at right angles to the torque arm. But if this f makes an angle theta, then the torque is produced not by the whole of this force, but the component of the force at right angles to the torque arm. Tell me, if the force vector makes an angle theta with the torque arm vector, what is the component of this f at right angles to that torque arm? It will be f sine theta. I hope you understand that. Yes. Now the component of this force at right angles to r is f sine theta. That's right. That means the torque is now produced by this component of the force. So what is the torque now? The torque now is r times f sine theta. So this is a general equation you can remember. When theta equal to 0, you see, when theta equal to 90 degrees, tau equal to r times f. In other words, sine 90 is 1. If theta equal to 0, that means the force and the torque arm are in the same direction. The angle between them is 0. That means that force cannot produce a rotation. Now tell me, why is the door handle kept away from the hinges of the door? When you pull on the door handle, do you see the door rotates? And what is the axis of rotation? It's the axis passing through the hinges. Have you ever tried to open a door by applying a force on the hinges? Will the door open? No. Why not? Because this angle theta is 0. The torque arm is 0. That force cannot produce a torque. So you must understand, torque is measured as the perpendicular component of the force. Perpendicular to what? Perpendicular to the torque arm. The torque of a force is the product of the torque arm and the component of the force at right angles to the torque arm. So what is the unit for measuring torque? Torque tau is measured in meter Newton. R, the torque arm, is measured in meter and the force is measured in Newton. So torque of a force is measured in meter Newton. Well, we already said the product of a vector of another vector at right angles to it is called the cross product of two vectors. The cross product of two vectors. Therefore, I can write the cross product of two vectors is a vector at right angles to both the vectors. In other words, if the vector, let me see if I can show that to you one more time. Let's take a look at our old example one more time. I want to produce rotation about this axis, and you can see I'm going to apply a force vertically down, and now this is the torque arm. That means, well, this is not the torque arm. What is the torque arm? The torque arm is this distance. The distance that is perpendicular from the axis to the force. This is the perpendicular distance. Therefore, the torque will now be the force multiplied by r sine theta. If this is r, this distance will be r sine theta, where theta is the angle between the force and the r vector. Well, we have the torque. As I keep rotating, the torque arm becomes smaller and smaller, right? And finally, when it comes to this position, the angle theta is 0. There is no more any torque there. The torque of a force is a vector quantity. Now, if you look at this, this is the r vector and this is the force vector, and they are contained, the r vector and the force vector are in the xy plane. The torque will be at right angles to both these. So the r vector, the f vector, they are both in the xy plane. Then the torque will be in the z plane. The torque is either directed towards me or towards you. It depends on the direction of the force. So if the force is downward, the torque will be directed towards you. If the force is upward, the torque will be directed towards me. You see? So when I rotate it like this, the torque will be directed towards me. Whereas when I rotate it in the opposite direction, the torque will be directed towards you. The direction of the torque will be perpendicular to both the direction of the force and the direction of the torque arm. So r times f sine theta, which is the torque produced by the force, is the cross product of vectors r and f. And we write it like this: tau equal to r cross f. And tau is a vector quantity. It has a direction. What is the direction of tau? The tau is directed at right angles to both the r vector and the f vector. Alright, the direction of tau is given by the right hand rule. What is the right hand rule? It says, okay, let's make the statement of the right hand rule. Keeping the thumb at right angles to 4 fingers. Now, these are the 4 fingers and the thumb is at right angles. You can see that. Keep the 4 fingers with the thumb at right angles. Now wrap the 4 fingers from R to F. Wrap the 4 fingers from R to F. Now that means if this is the r vector and this is the force vector, look at this, the r vector, this is the r vector, this is the force vector. What you need to do is now wrap your fingers, wrap the four fingers from R to F. Four fingers wrap from R to F. Then the thumb will give you the direction. That means if you now rotate, if the rotation is like this, the torque will be directed towards me. If the rotation is the opposite direction, the torque will be directed towards you. So the direction of the torque is actually determined by the directions of the r vector and the f vector. Okay, let's now look at a problem. The figure shows a crowbar used to remove a countertop. Now, very familiar example, is that right? This is the countertop and you use a crowbar which is something like this, which has a bent end. I can insert the bent part under the counter and apply a force directed downward to produce a rotation. That means I am producing a torque. The workman applies a force of 50 Newton vertically down at a point 60 centimeter from the fulcrum. Actually, the fulcrum is where the crowbar is, the end of the crowbar is resting on the countertop. That is the fulcrum. Fulcrum is the point about which the rotation takes place. Now, if you insert it there and move it, well, this is the fulcrum. The fulcrum is the point about which the rotation takes place. Find the torque produced by the force about the fulcrum. The crowbar makes an angle 30 degrees with the vertical. Alright, let's understand this problem a little more. R equal to 0.6 meter. You understand that the length of the crowbar is the torque arm. So that R, the R vector, this is our R, and that is 0.6 meter. And F equal to 50 Newton is acting vertically down. Now, that means if you look at the R vector and the F vector, the torque arm will not be the whole of R here. The torque arm will be this distance. Now look at that. If I bring it all the way down here, it will be this distance, which will be R sine theta. What is the angle? The angle R makes with F is 30 degrees. Now, tau equal to R cross F. And what is the magnitude of this cross product? The magnitude will be R times F sine theta. It will be R times F sine theta, because the component of this force at right angles to the crowbar will be F sine theta. So it will be R times F sine theta, that is 0.6 times 50 sine 30, that is 15 meter Newton. Okay, that is a very important concept here, that the magnitude of the tau, the cross product, is R times F sine theta. Remember I told you it is F sine theta that is at right angles to R. So it is the component of this force at right angles to the R vector that actually produces the torque. So torque is R times F sine theta, that gives you 15 meter Newton. Alright, let's now talk about another concept called moment of inertia. Moment of inertia. A very important concept in rotational motion. Well, I'm going to develop that by taking a disc like this. Now, suppose I have a disc that I want to rotate. You can see I can rotate this disc about this axis. Look at that. This is the axis. And if I apply a torque, I'm applying a torque and rotating the disc. Now, when this disc rotates, every point object on this disc can be considered to be made up of thousands and millions of particles. And we can consider the motion of each of those particles. Each particle will be subjected to a force, and that force will produce an acceleration. Alright, let's look at that in a little more detail. Now, here is the disc that I have just been showing you. Consider a disc of mass m and radius r rotating about an axis. So the disc is rotating about an axis. Can I say the disc is rotating in the clockwise direction? I hope you understand that. The direction of rotation is the direction of motion of the hands of a clock. So the disc is rotating in the clockwise direction. A point mass m1 at a distance r1 from the center. Let's say this is a point mass of mass m1 and its distance is r. We have a point mass m1 at a distance r1 from the axis. If a force F1 is acting on that mass m1, that force F1 will produce on it an acceleration a1 according to Newton's second law of motion, F net equal to ma. Is that right? So a force F1 acting on this mass m1 produces an acceleration a1. This force F1 produces an acceleration on this mass given by F1 equal to m1 a1. Well, if alpha is the angular acceleration of the disc, when the disc is rotating, it will have an angular acceleration. If alpha is the angular acceleration, you know how it is related to linear acceleration. You know that A equal to R alpha. So A1 equal to R1 alpha. Therefore, we can say F1, the force acting on this point particle, is m1 r1 alpha, where m1 is its mass, r1 is the distance of the point from the axis of rotation, and F, the force, is at right angles to that distance. Alright, what is the torque of this force about this axis? Tell me, what is the torque of this force F1 about this axis? It will be the torque arm, which is R1, times F1 sine theta. Theta is 90 degrees, therefore sine theta is 1. So we can simply write it as tau 1. Tau 1 will be the torque on this particle. Will be R1 times F1. So tau 1 is R1 times F1. Now remember, the sine theta becomes 1 because angle theta is 90 degrees. And replace this F1 by this quantity. F1 is m1 R1 alpha. So that will be R1 times m1 R1 alpha and that will be m1 r1 squared alpha. This is the torque on this minute particle of mass m1. That means if you now take any other particle on that rotating disk, there will be a similar torque on that particle. So let's consider now another particle, a force F2 acting on a point mass m2. This is a point mass m2, and a force, now this m2 is at a distance r2 from the axis of rotation. A force F2 is acting on it. What is the torque on this particle? It will be R2 multiplied by F2. Is that right? Tau 2, the torque on this particle, well, the torque is rotating that particle, will be R2 times F2. And what is F2 equal to? If F1 equal to m1 r1 alpha, then F2 will be m2 r2 alpha. Will alpha be different for these two particles? We had talked about it earlier. You see, because the radius rotates, as the radius rotates, it describes the angle. That means the acceleration, the angular acceleration of any particle on the disk will be the same. Why? Because all the particles describe the same angle in a given time. Therefore, this mass m2 and this particle of mass m1 and any other particle on the disk will all have the same angular acceleration, which is alpha. So the mass of the particle may change. The mass of the first particle is m1, the mass of the second particle is m2. The first particle is at a distance r1 from the axis of rotation. The second particle is at a distance r2 from the axis of rotation. But the angular acceleration of any particle on the disk is all the same, namely alpha. So tau 1, the torque on the first particle, is m1 r1 squared alpha. Tau 2, the torque on the second particle, is m2 r2 squared alpha. The torque on a third particle will be m3 r3 squared alpha, and so on. If you now take an ith particle, what's an ith particle or nth particle? The torque will be mi ri squared alpha. Let's write that down. The disk is made up of thousands of such point masses. If tau I is the torque on the ith particle, well, for this particle that I equal to 1, for this particle that I equal to 2, that I can have any value. If you take the 100th particle, then that I will be 100. So if tau I is the torque on the ith particle of mass mi, what will be tau I equal to? Tau I will be mi ri squared alpha. Okay. The total torque, therefore, will be the sum of the torques of all these particles. Is it not so? Does it make sense? I think so. The total torque tau on the disk. We have now obtained the torques on each individual particles. If you know the torques of all the particles that compose the disk, then the total torque tau on that disk will be the sum of all these torques. How do I write it? Tau equal to tau 1 plus tau 2 plus tau 3 plus tau 4 and so on all the way to tau I, depends on how many particles are there. And we can write it like this: tau equal to summation tau I. Summation tau I. Add all the torques on all the particles. That will give you the total torque on the disk. Alright? And this tau I is mi/ri squared alpha. So we say tau, the total torque on the disk is summation I mi/ri squared alpha. What does this mean? It means m1 r1 squared alpha plus m2 r2 squared alpha plus m3 r3 squared alpha all the way to the last particle. Now, you know that m and r are different for different particles, but alpha is the same for all particles. The angular acceleration will not be different. They will be the same for all particles. Therefore, I can take this alpha and keep it outside the summation. So I can write it as alpha times summation I mi/ri squared. And now, this quantity summation I mi/ri squared has great significance in rotation. What is the significance? Summation I mi/ri squared is called the moment of inertia of the disk about the rotating axis. Now there are a couple of information that's important there. Moment of inertia of a rotating object is always measured about an axis. You see, the moment of inertia of this rotating disk, the expression here, summation I mi/ri squared, is the total torque of the whole disk about this axis. You see, this is the axis of rotation. If you want to take the torque of the same disk about another axis, it will be different. You see, the moment of inertia of an object is defined about an axis. If you change the axis, the moment of inertia will change. Well, I will show that in a minute. So what is summation I mi/ri squared called? It is called the moment of inertia of the disk about the axis of rotation. What is the unit for moment of inertia? Moment of inertia is represented by I and is measured in kilogram meter per second squared. So, let me ask you, if a point particle is rotating about an axis, if this point particle m1 is rotating about the same axis, what is the moment of inertia of this particle about that axis? The moment of inertia of this particle about this axis is m1 r1 squared. The moment of inertia of this particle about that axis is m2 r2 squared. And add the moment of inertia of all such particles. That is what we call this. Summation I mi/ri squared is the moment of inertia of the disk about its axis of rotation, and it is measured, look at this, kilogram meter squared is the unit of moment of inertia. We can now write an equation for torque I. Now look at this, torque, we have the equation torque equal to alpha, the angular acceleration, multiplied by this quantity. What is this quantity called? This quantity is called the moment of inertia, and we will represent it by the uppercase I. And therefore, I can now write tau equal to This is called I. That will be I times alpha. And that is the equation for rotational motion. Now tell me, what is the corresponding equation in linear motion? This is the rotational motion, tau equal to I alpha. The corresponding equation in linear motion is F equal to ma. You see that? Linear acceleration is produced by a linear force. A rotational acceleration is produced by a torque. So tau equal to I alpha takes the place of F equal to ma in translational motion. Alright, in that case tell me, what is the role of this I, the moment of inertia? If you noticed, in linear motion our equation will be F net equal to ma. In rotational motion, that equation becomes tau net. The best way to write this is tau net. The net torque is equal to I alpha. Look at that. F net is replaced by tau net. Linear acceleration A is replaced by angular acceleration alpha. And therefore, this moment of inertia for rotation correspond to mass in linear motion. You see that? The moment of inertia in rotational motion is a quantity that corresponds to mass in linear motion. F net equal to ma, tau net equal to I alpha. So you must understand that relationship. Alpha is the angular acceleration caused by the torque. Now this is similar to F equal to ma for linear motion. Okay. The moment of inertia I plays the same role in rotation as m plays in linear motion. Now, what is the moment of inertia of a disk? Now remember, moment of inertia is defined about an axis. Now let me see if I can spend some time. Now here I have an object of mass m, and I'm going to rotate it about this axis. You see, the axis of rotation is this. That is the axis of rotation. That means this is r, the perpendicular distance between the mass and the axis. And therefore, what is the moment of inertia of this particle about this axis? It is mr squared. Now, if I change the position of this mass over here, I am changing the moment of inertia. You see that? Now it is much easier for me to rotate. The moment of inertia is now less. mr squared is less. If I move it out, I'm increasing the distance r, and this moment of inertia is now greater. Now you can see I have to actually use a greater force to keep it rotating. The moment of inertia of this mass is now greater. Now, moment of inertia is always defined about an axis. Well, let's look at this disk. Now, it is easy for me to rotate this disk about this axis. Look at that. Now, this disk has a moment of inertia about this axis. You can see the axis is actually passing through its center of mass. And so, the moment of inertia of this disk about the axis that passes through the center of mass, we will call I center of mass. Moment of inertia of the disk about an axis that passes through its center. Now, can you imagine if I want to rotate this disk about an axis passing through here? Well, I'm going to hold it there, and how difficult it is for me to rotate it about that axis. That means this disk has a much greater moment of inertia about this axis. The moment of inertia of a disk is the least about an axis that passes through its center of mass. If you take any other axis, the moment of inertia of that object about that axis will be greater. We will look at that in the next part of this lesson. Now look at the meter rule here. I can rotate this meter rule very easily about its center of mass. That means its moment of inertia is the least about its center of mass. Suppose I want to rotate the ruler. Now, if I want to rotate the ruler about an axis, suppose I want to rotate this ruler about an axis passing through this point. How difficult it is. It is very difficult. That means the moment of inertia of this ruler about this axis is much greater than its moment of inertia about the center of mass. Okay, now you need to remember a couple of formulae for moment of inertia of certain regular shapes, and I'm going to give you that formulae. Okay, well, first of all, let's consider a disk. A disk is the most commonly used device for rotational purposes. So a disk and its axis passes through the center of mass. This cm stands for the center of mass. It has a radius r and a mass m. The moment of inertia of a disk of mass m and radius r about an axis that passes through its center of mass. Now, the formulae I'm going to give you now are all the moment of inertia of regular objects about an axis that passes through their center of mass. Now, what is the formula for the moment of inertia of a disk about an axis that passes through its center of mass? The formula is this: I center of mass equal to 1/2 mr squared. This is the moment of inertia of a disk of radius r and mass m about an axis that passes through its center of mass. Well, this is an axis passing through the center of mass of this disk. So its moment of inertia is 1/2 mr squared. Alright, let's look at the next regular shape. The moment of inertia of a sphere. If I have a sphere like this, and look at the axis. Its axis is passing through the center of mass. And the center of mass of a sphere of radius r and mass m about an axis passing through its center of mass is 2/5 mr squared. You should be able to use these equations wherever they are necessary. Okay. Another one. What is the equation for the center of mass of a ruler like this, which has got a length L and a mass M? The I center of mass. What does I center of mass stands for? The moment of inertia about an axis through its center of mass. So I center of mass for a ruler like this about an axis through its center of mass is 1/12 ml squared. And finally, what is the moment of inertia of a hoop? That will be I center of mass equal to mr squared. We rarely use this, but a disk, tell me, what is the moment of inertia of a disk about an axis through its center of mass? 1/2 mr squared. What is the moment of inertia of a sphere about an axis through its center of mass? It's 2/5 mr squared. And what is the moment of inertia of a ruler about its center of mass? It is 1/12 ml squared, where L is its length. Well, what we have done is we have now discussed some fundamental ideas of rotation. We now know that the second law of motion is equally applicable to rotation. F net equal to ma can be replaced by tau net equal to I alpha. And you should have a good understanding of what that I, moment of inertia of an object, is. I'm going to stop this lesson here, on this part of the lesson. I'm going to take up another part for this lesson. We will continue discussing moment of inertia. Okay.